In this video, we'll talk about vector-valued functions. So, vector-valued functions, they are functions that they look like this. So you could have, so instead of your usual function being written with italic, you have boldface, right? Which denotes the fact that it returns vectors. So a vector-valued function, it takes in a real number, which you can think of as denoting time, and it returns out a vector, okay, which you can see in the expressions here. So this returns a two-dimensional vector, this returns a three-dimensional vector, or well, a vector living in 3 space, a vector living in 2 space. It's a bit wrong to say that vectors have a dimension, I think. Although it makes sense what I mean by that. So then we also call these parts that make up the vector value function, the component functions. See, if we restrict ourselves to the x component, we would just have the function f. Restricting to the y component, we would have g, and the z component, we would have h. So they describe the way that the function r moves in with respect to those 3 axes individually. Okay, and so this is using the standard unit normal, standard unit vectors, whereas this uses the component form. So another way we can write vector-valued functions is in this component form. And another thing we'll need to know is the limit of a vector-valued function. So the notion of limit typically requires you to know the notion of continuity. The story is exactly the same as in Calc 1, except we just have extra dimensions to work with. So a function is continuous if all of its arguments are going to be continuous, right? A vector value function is continuous at a point if all of its component functions are continuous at the point. And the limit of a vector valued function is the limit of the component functions, as you can see in this formula. Now to do some examples. So suppose you have this vector valued function, and you want to take the limit as t goes to 3. So we just end up splitting limit over each of the 3 component functions. So we end up taking the limit of the component function in x, component function in y, component function in z, and each of these limits should be pretty straightforward. I believe you can plug into all of them. Yes. So here you'd get 6 minus 4, you'd get 2 on top, 4 on the bottom, which simplifies to 1/2. Here you'd get 3 over 10, and here you'd get 12 minus 3, which is 9. Okay. This problem, well, we have 4 parts to it. The first 3 are really similar to each other. They're very related. So when you are thinking of taking the limit, well, to do this rigorously, thoroughly, what you'd do is you'd actually split the limit operation over both component functions, and then you'd compute those limits, which of course these are continuous functions, so you could just, the way you would take the limit is you'd plug in, and so you'd end up with a vector of 5, 15. Versus if you were to just evaluate this vector valued function at 3, you would end up just plugging in it directly. So, and the reason that these two agree with each other, the reason there's no issue with that, is because the function is actually continuous at 3, right? Each of these functions are, well, these functions are specifically continuous everywhere on the entire real number line, so they're continuous at 3. And this last one perhaps is just beginning to set us up for the derivative, which we'll see in the next section. So we have r of t plus 1 minus r of t. Well, this expression returns a vector, and this expression returns a vector. So this subtraction is the subtraction of 2 vectors, right? If we expand out these expressions by just using the definition for the r of t, we would end up getting this for the first expression, r of t plus 1. And of course, we subtract off r of t. Then what we do is, well, vector subtraction, the way you normally do vector subtraction is you subtract each of the component functions. So the x component function minus the x component function, and the y component function minus the y component function. So when you do that, you will end up with this. I also distribute, or I expand, so we get t plus 1 quantity squared gives me this t squared plus 2t plus 1. Then we subtract off minus 4 also, and then minus the quantity t squared minus 4. And that's all the x component function. The y component function, you get 4t plus 4 plus 3 minus the quantity 4t plus 3. And then cleaning this up, getting rid of common factors or common terms, you'd get the vector 2t plus 1 comma 4. Okay. The next example is pretty much the same idea. This time, instead of the limit going to a number, it's going to infinity. So, but taking this limit is the same as taking limits in Calc 1. So, limit of each of the component functions. Now, I would hope it's clear how you take the limit of each of these, but let's just maybe make sure that we can see that. So this exponential function has a negative in the numerator, which means that we can rewrite this as e to the 2t in the denominator. And so we're taking the limit as t goes to infinity. And so notice that it would go to 1 over infinity, which is 0. Right? The denominator blows up to infinity, so the whole fraction goes to 0, which gives us the first term there. The limit of the second function, as t goes to infinity, notice that this is a rational function, right? It's a polynomial divided by a polynomial. And you know that its end behavior is determined by well, it's based around the degrees of the two polynomials. So the fact that these two polynomials have the same degree means that this limit, as t goes to infinity, it's going to be the ratio of the leading coefficients, so 2 over 3. Or you could do this in the more rigorous way of actually, say, dividing the numerator and denominator by t, and then taking the limit as t goes to infinity. You could do it that more rigorous way, but the intuitive pre-calculus way is I think we all prefer that. It's the easier way to think about things. The limit for the last function requires you to know what the inverse tangent function looks like. So you should hopefully have this kind of picture in mind of how inverse tangent behaves. It has these two horizontal asymptotes at pi over 2 and at minus pi over 2. So we're trying to take the limit as t goes to infinity, which makes us approach this horizontal asymptote. And so we end up getting the value pi over 2. Right? This 2 inside the inverse tangent function just makes us go approach infinity faster. It doesn't stretch this, well, it stretches this horizontally, which doesn't matter for the ending value of the inverse tangent function. Okay. Right. Then you have a problem that asks for the domain of a vector valued function. So the sensible thing to do is it's going to be the intersection of the domains of the component functions, right? In order for the vector valued function to be defined at some value t, it has to be defined on each of the component functions. So we would figure out the domains of each of these functions, and we would take the values in common between all of them, take their set intersection. So in particular, this one, you can see that this asserts that t must be greater than, or no, it has to be strictly greater than. It can't be equal because then you'd have a 0. So t must be greater than 3. In this one, well, the natural log function looks like this. Ln of x, let's say. So natural log is defined from 0 to infinity, excluding 0. So this one would actually give you the value that t must be greater than 2. And with this, cosecant you should know is equal to the reciprocal of sine. And so the problematic parts are when sine of t is equal to 0, which occurs at multiples of pi. Right? Thinking about the sine function, I was drawn kind of badly. So the sine function is like this, and its zeros are at, you can see, pi and 2 pi. So the zeros of the sine function are at integer multiples of pi, and these are the problematic points. So that's why we end up having our domain be the intersection of these things. So we must have t be greater than 2, t be greater than 3, those combine together to be just t being greater than 3. And also, t cannot be an integer multiple of pi, which is this last part. So this is the domain of this function. I specifically chose a problem that is a bit more challenging than your homework problem. I believe your homework problem is quite simpler than this. So, yeah, but it's good to see a complicated example. Okay, is this the last problem? Yes. So, in this one, we are asked to eliminate the parameter t and then write this in Cartesian coordinates. Yeah, because this way of expressing the the function is more like a parametric form. You've kind of isolated things into being like a function of x and also a function of y, right? This is like the x component, this is the y component. So this vector valued function way of writing things is kind of a parametric form of expressing a curve in, well, in this case in two-dimensional space. But it's a curve, and certainly if it can be expressed as a function, it can. There's a process to try to eliminate the parameter t to make it written either implicitly or explicitly as a function, as y a function of x or x a function of y. So in this case, we are able to actually write it as a function of x, right? So notice that this is the function for x, so I write it like so, and this is the function for y, so I write it like so. And then by solving for t in the first equation, right, we just divide by 2, we are able to then take this and plug it into the equation for y. So that just requires us to square t, so we end up with this. So that gives us the equation y equals x squared over 4. So this is the equation that we can plot. This is a way to express this vector value function instead of in this parametric form in a Cartesian form. And of course, I sketched it below. And that's all I've got.